All right, to finish off Unit 6, we're going to take a section 6.6 and 6.7 actually, and instead of dealing with probability, they're going to deal with what's called a series. So we have this little honors topic that we need to cover, and it doesn't quite fit in any unit particularly, so we just put it at the end of Unit 6. So 6.6, our objective today is to calculate what's called sums of arithmetic and geometric series. So both these words should sound familiar because in ninth grade, we do go over a whole unit on sequences, both arithmetic and geometric. Well, now this year, we're going to take it just a little bit further, getting us more prepared for future classes and look at what's called a series. So let's just kind of remind ourselves a little bit in our warm-up. It says a sequence is arithmetic if a series of numbers has a common difference. So if we can find a pattern, a common difference would either be if they were adding or subtracting. And a sequence is said to be geometric if a series of numbers has a common ratio. So that's if we can find a multiplication pattern. So we want to find the common difference or ratio for each of these. So personally, I tend to look for a common difference first. And then if I can't find a difference, I usually look for a ratio. So to find our difference, we're just essentially taking a number and subtracting it from the one in front. So 4 minus 2 is 2. 6 minus 4 is 2. 8 minus 6 is 2. So it looks to me like our pattern would just be adding 2 as we progress. So we would call this a common difference, and we use the variable d for common difference. Our common difference, our pattern is just adding 2 each time. Where number 2 kind of starts off the same way, but noting that it goes 2, 4, 8, I'm feeling more confident that this would need to be multiplication. And sometimes ratios can be harder to find. So to find a ratio, we usually take a number and divide it by the term in front. So in this case, a 4, which tells me that my ratio would need to be 2. So a common ratio, what we're multiplying by, is R. So ratio for that multiplication pattern. Problem 3, we notice that the numerators are staying the same, but those denominators have the multiplication that's happening. So we're going from 4 to 8 to 16. So I'm seeing the pattern of timesing by 2 in the denominator. So I definitely feel like this is a ratio, but because my numerators are staying the same, I would just put a 1 in that numerator. Okay, problem 4. Looks like it's decreasing, first of all. It's going from 28 to 24, so that would be a subtraction. And then 24 to 20, so that's also a subtraction of 4. So I feel like this is a common difference, subtracting 4 or adding negative 4, which you could think of either way. So really quick kind of reminding us about those two kinds of sequences. Let's go ahead and look below this warm-up and learn a little bit more and review a little bit more. So first of all, we're going to highlight a few things in this vocabulary box, first of which is a sequence. So remember, a sequence, we would name something like a sub 1, a sub 2, and those sub numbers are referring to the index where they are in the sequence. So a sequence is a list of terms in a specified order where a sub 1 is the first term and a sub n is the nth term or the general term. So a finite sequence has a first term and a last term. So in the warm-up that was given, all of these had ... So they were going on past what we could see. So we weren't dealing with a finite sequence. We were dealing with an infinite sequence. It has a first term, but it's maybe going to continue without end. In a series, we look at all of those terms and we find their sum. So a series is the sum of all those terms in a sequence. So we take a sub 1 plus a sub 2 plus a sub 3, etc. So we can take a series and have a finite series, which is the sum of terms with a finite sequence. So if it has a first and a last term. Or we can find a sum of an infinite series, which is just a sum of all those finite sequences, or infinite, sequences, which is a little bit of a bigger concept, which you'll definitely cover in some future classes. Geometric was one of our types of sequences. So a geometric series is the sum of the geometric terms in a sequence. So we see a similar relationship. In an arithmetic series is the sum of the terms of an arithmetic sequence. So we notice in both of our sequences, in our ratio, we're timesing by something, but in our arithmetic, we're adding, which is the difference between those two types of sequences. So we're going to be finding the sum of some series today, which means we're ready to get a new Greek letter. And the Greek letter we're going to get is the capital letter sigma. So when I'm trying to draw sigma, and some of you may be better at this than I am, I usually just try and draw kind of a block sigma, something like this. If you feel like you can do it a little bit better or different, feel free, but that's generally what our sigmas look like. And these are used to indicate the sum. So anytime we see this, we know that we're supposed to find the sum. So it says in the next sentence that the sigma is followed by the explicit form of the sequence, which we practiced a lot of explicit forms last year. So we have an example down here. We see the summation symbol, our sigma, and then we see a 2k plus 1. This is an explicit formula. We know we can plug in for k, and we could get an output. We notice above and below our sigma, we have some different notations. It says the small number below the sigma is the first term, or it's called the lower limit. So we want to start with the first term. And then the smaller number above the sigma will be our last term. So do we want to go the 10th term or the third term or whatever term we want to add to? And that's called our upper limit. So we can take these and we can find their summation. So let's look at an example of our summation. So here we have our sigma notation, and we're supposed to be going from k equals 3 to 7. We see our explicit formula as k cubed. So we're going to be replacing k with values from our notation, our lower limit to our upper limit. So I'm going to start with 3 because that's my smallest. So I'm replacing my k with 3 cubed. Plus, this is a summation, so we're adding this together. My next value would be 4 cubed plus 5 cubed plus 6 cubed plus, and 7 is my last k value that I'm going to substitute in. So I type all of this into my calculator, and I get the summation of those those 5 terms to be 784. If we were to have an infinite series, which we're not going to deal too much with some infinite this year, the upper limit would end up to be infinity. So instead of having a 7 on top, we'd have an infinity symbol. So that's definitely something that's coming our way. So let's try a little bit ourselves. Example 1 wants us to write out and evaluate each of these sums. So we see our summation, our sigma. Looks like we're going from k equals 2 to 6, and I can see my explicit equation. So I would like to write out all of my terms here and then find my solution. So I'm going to take 3 times k, so my first k is 2, and then plus 1. So all of that needs to be added to my next term. So my next term, I still have 3, but my next k value, I just used 2, so that would be 3 and then plus 1. Plus 3 times 4 plus 1. Plus 3 times 5 plus 1. Plus 3 times 6. And 6 was our biggest k value we were plugging in. So now we need to evaluate. If you want to try and do some of this in your head, you can. If you want to punch all of it into your calculator, you can. I think I can do some quick multiplication. I know that this one's going to simplify to 6 plus 1, so 7. 9 plus 1, that'll be 10. 12 plus 1, 13. 15, whoops, so that was supposed to be a plus. 15 plus 1 is 16, and 18 plus 1 is 19. So I'd like to add all those together. 7 plus 10 plus 13 plus 16 plus 19. And I get a total sum of 65. So all of these terms, starting from term 2 to term 6, when we plug into this function, have a sum of 65. Let's try it again for the next one. Similar to the one we saw above in the example, except now we have 3 to the k. So we're going from 2 to 5, so I'm going to start my summation here. 3 to the k, well, my first k is 2, plus 3 to the k, my next one would be cubed, 3 to the fourth, and 3 to the fifth. We could try and simplify a little bit here, but it's probably just as fast to type this one in. So let's see, 3 squared plus 3 cubed. Make sure you bring your cursor down there. Plus 3 to the fourth, plus 3 to the fifth. Now all these are exponential, so I'm not shocked that I get a pretty big value, 360. So part of your assignment today will be to write out, similar to what we just did, and find the summation of some different explicit formulas. So let's go ahead and turn the page. Of course, once we learn how to do something by hand, we have to learn if we can do something with technology, which would make complete sense that somebody's figured out how to add these without us having to do it all by hand. So at the top here, I've got some instructions, especially if you're using a TI-83, I would walk through these directions because yours will have a little bit different operating systems. The TI-84s would also work on this too, but most of the newer TI-84s have an update on them that actually lets you do this a little bit faster. So I'm going to just put here, if we wanted to do this a little bit faster on our calculator, we could press the green alpha button, which I'll do in a second. And then we would press the window button, which is right underneath our screen. And then we'll choose number 2. Or I'll show you another way too. You could press the math button, which is on that left side of our calculator, and then choose 0. So let me bring up my calculator here. So if I want to find my summation menu to be able to evaluate, I can press alpha and then the Windows button, and it pops up some options here. And number 2, we see our sigma for our summation. So I'm going to go ahead and press enter on there. And then I can type in whatever values I may need. Let me show you the other one too. So the other one says I can press math. So I press math and I have to choose 0. Well, I can't see 0, so maybe I press my up key and it gets to the bottom faster. And there's that 0 and it says summation. So I can get to it either way, but if you've got an updated one, that alpha y equals takes you right to that menu. But either way, I think they're both pretty fast. So we can find let the calculator find our summations for us. So example 2, that's what we want to do. We want to find the summations. Now, I use K because that's what the district materials that they gave us used K, but really you could use any variable. And for the calculator's sake, it's probably easier to type in X. So I'm going to call it X instead of K. So for this problem A, we have that K equals 5, so X equals 5. And notice it's got a right arrow, and when you press that right arrow, it takes you up to that upper limit. In this case, it's 20. Aren't we glad we don't have to write out all 20 of those? Again, right arrow takes me down to be ready to put in my explicit equation. So we have 2K minus 3. So again, I'm going to do it 2X minus 3. So by pressing enter, it'll automatically find the summation for us. 352. If we take all of those sequence terms from 5 to 20 for this linear function. Let's try it again on B. This time we're going from 4 to 42. Again, aren't we glad we're not typing that in? I'm going to do alpha y equals and choose that number 2. Whoops, I forgot to type anything in. Let's see, X, my lower limit is 4. My upper limit is 42. And I have negative 4x plus 5, my next linear function. Oh, I'm not really shocked that I got a negative value because my rate of change there was a negative. So it's okay to get negative values. Negative 3,393. Let's look at C. This one's exponential, so I'm going to go ahead and just clear that, alpha y equals, and choose that number 2. K, or x, is equal to 1 in that lower limit, but my upper limit is 5. And we have negative 5 being multiplied, whoops, I wrote divide, multiplied to 2 to the x. So negative 310. Punching it into the calculator saves us a whole bunch of time versus writing it out by hand and doing the calculations all by hand. Alpha y equals number 2, x, our lower limit is 1, our upper limit is 8, and we're taking negative 2 times, and you could put parentheses, I'm just putting times, and you can put this as a decimal if you wanted to. You could put 0.5 just for sake of one less thing to type, to the x. So this one's not a whole value. So I would try first to see if it'll change it back to a fraction. If it won't change it back to a fraction, then you're welcome to leave it as a decimal. But if I do my alpha y equals and choose number 4, this one will change it back to a fraction. It's not pretty, but that's what it is. So negative 255 over 128. So part of your assignment, I want you to be able to write these out by hand. And then part of your assignment, I want you to be able to use your calculator. So that'll be a nice section. The last thing that we're going to do is we're going to practice writing our own summation. So as a reminder, from last year, when we're looking at an arithmetic sequence, here's our explicit formula. So we normally would see something like y equals mx plus b for a linear function. But in a sequence, we realized last year that difference, that pattern of either adding or subtracting, was the same thing as our slope. And a sub 0 was our y-intercept, so that was our b. So same idea, just different letters because it's in sequences. So how do I find my difference? Remember, you just have to take a term and subtract it from the one in front of it. So if you can't see the pattern, you can do that. And how do we work backwards in a pattern to find an a sub 0? So a sub 0 should come before a sub 1. So if I take my first term and subtract the difference that I found, I should be able to work back in my sequence. So arithmetic sequence is a little different than geometric. Geometric, we know, has to have a multiplication. So we see that we have our y-intercept, that a sub 0, gets multiplied to our ratio to the n power. So we have to be able to find our ratio. So we can take any term and divide it by the term in front of it. That'll find our ratio if we're not sure. And then to find our a sub 0, we just have to take the first term and divide by the ratio this time instead of multiplying to go forward. So those are kind of a quick reference if you need to refer back to them because it has been a little while for us. So remember, in a sequence, as we're looking at example 3, this would be a sub 1, a sub 2, a sub 3. They always start with a sub 1. And technically, notice it says dot, dot, dot. There should be a plus right there. Dot, dot, dot plus 24. So I don't know what space or what item number this is, what number in the sequence, but I know it's the last term. So I need to find out a little bit more about my sequence before I can write my summation. So first of all, what's my pattern? So I'm noticing that it's increasing by 3. So I'm feeling pretty confident that this is a common difference because we're just adding 3. According to my explicit equation, I need my common difference, that slope, that rate of change, but I also need my intercept. I need my a sub 0. So if adding 3 takes me forward in my sequence, I can work backwards by subtracting 3. So if my first term is 3, then 3 minus 3 would be 0. So as far as my explicit equation, I just have my rate of change times, I'll keep using k, but you could put any variable really there. But my intercept is just 0, so we probably wouldn't write that. What I do know is that my last term is supposed to be 24. So if I take my explicit equation and set it equal to that last term, I can divide by 3 in this case, and that tells me that the 8th term in my sequence should be 24. So by taking my explicit equation and set it equal to that last value, I can solve for what term in the sequence it is. And I need that because I need to have a lower limit and an upper limit on my summation. So let's try drawing your summation. My lower limit is always going to be 1 for us right now. We're not going to get into when is it not 1, when it is it. So we'll just assume that all of our lower limits are 1 for this year. And I just solved for my upper limit. K is going to be 8. My explicit equation, I already had here that 3K. So if I wanted to find the summation of all of these numbers, I would have to go from 1 to 8 for this linear equation there. Let's try it again on B. So again, this is my first term, my second term, my third term, and I just don't know that last term. So what's my pattern? It looks like it's decreasing from 12 to 9. That's decreasing by 3. 9 to 6. That's also decreasing by 3. So I'm feeling pretty confident that my pattern is minus 3 this time. So to find my a sub 0, my y-intercept, I have to work backwards. So this time subtracting 3 takes me forward in my pattern. So adding 3 will take me backwards. So 12 plus 3 puts my intercept at 15. Now I have enough information to write my equation to help me solve for K. So I have my rate of change and I have my intercept. And together, there's some value of K that's going to give me a negative 15. So this time, if I subtract 15 and divide by negative 3, I get a value of 10. So 10 has to be my upper limit. So on my summation, I'm supposed to be going from K equals 1 to K equals, 10. On my function, my linear equation, that explicit form, negative 3K plus 15. Let's look at problem C. I'm already feeling like this can't be arithmetic because look at that big number, 16,384. So what would be my pattern? I'm looking from 4 to 16. That feels like it could just be multiplying by 4. And 16 times 4 is 64. So I'm feeling pretty confident that I have a common ratio this time, which is 4. I still am given the first term, the second term, the third term, and the a sub n term that I need to find there. So that means to find my a sub 0, I have to work backwards. With my pattern is to multiply by 4, I need to divide by 4 to work backwards. Well, 4 divided by 4 is 1. So in my exponential equation, as it says above in our table, our explicit form says to take our a sub 0, which is a 1, times our ratio 4, and that gets taken to the exponent, which I'll call k again. So this time, I know my last term is supposed to be 16,384. So unfortunately, we do not know how to solve an equation yet for an unknown variable. Next year in secondary 3, you get to do that. So we just need to do a little bit of guess and check. I don't really need to type in my 1 because it's just times by 1. So I'm just going to focus on 4 to some exponent. It's a pretty big number, so maybe I start pretty big, like with a 6. Oh, that's good, but let's go bigger. What about 4 to the 8th? Oh, too big. 4 to the 7th. Ah, there it is. So if our K value is 7, or when our K value is 7, that upper limit, then we get that 16,000 number. So this time my summation still starts with 1, but it's supposed to go to 7 to get that last value. And you can leave the 1 on your exponential geometric explicit equation here, or you can drop it off. I'll leave it there just because I already have it written. Okay, last one, we've got some fractions. And I'm noticing my numerators, are staying the same. It's my denominators that are changing. They're getting bigger, and it looks like we're just multiplying by 2. So I'm feeling pretty confident my ratio this time needs to be 1/2. So to find my a sub 0, my intercept, I have to work backwards, and I have to take 5 over 4 and divide it by 1/2. which is going to end up giving me 5 over 2. So the 5 should stay the same. I'm just taking really half of that denominator. So I've got my intercept, 5 over 2, times my ratio, 1/2 to the k. So there's my explicit. And to help me find k, I need to set that equal to 5 over 64. So again, I don't have the option of trying to figure that out, so I'm going to have to do a little guess and check. So I'm going to type in my fraction there, 5 over 2, and then I'm going to put in parentheses the fraction 1/2. You could put the decimal, I guess, 0.5. And all of that we need to start testing. So maybe I test, I don't know, test 4. Getting close. I just need a 64, so I have a feeling it's the next exponent. So maybe I go back up and I copy that again and I go change that to a 5. 5 over 64. So if k is 5, then we get that 5 over 64 term, which means to write my summation, I know my lower limit is 1 and my upper limit is now 5 for this exponential geometric sequence here. So this is all we're going to do with series today, is to be able to find their sum either by hand or with a calculator, and then to be able to write your own summation using the sigma notation. So go ahead and self-assess, and good luck on your assignment.